So in this video, I will briefly talk about the notion of infinite Galois theory. So mainly I will prove the correspondence theorem, or sometimes they say the fundamental theorem. So I will start with recalling the notions of finite Galois theory, and let's see how we can proceed from there. So we start with finite field extension. Let's finite field extension. So this is said to be Galois if there are various equivalent statements about when an finite extension is Galois. So one of them is if it's normal and separable. Another one is if you look at the fixed field of this will be just and another one is it's K splitting field of a bunch of separable points. And the fundamental theorem, in case the actual extension is finite, uh, it says there is a projection between the subgroups of, let's say, this Galois group, which is nothing but the set of key automorphisms which fixes small pointers. So it forms a group, of course, under composition of maps. So it makes sense to talk about the subgroups. And the fundamental theorem says there is a bijection between those subgroups and the intermediate fields, which is sandwiched between small k and big K. And the correspondence goes like this. So you take a subgroup and you look at the fixed field, meaning all those elements of big K that is fixed under the action of H. And in the other direction, what you do, you just take in this intermediate field and you look at this. So firstly observe that this group is indeed a subgroup of this because the elements here are those when you restrict it to E just identity. Right? So these are in particular elements when you restrict it to K becomes identity as well because small k is contained inside. So it's a well defined map in both direction and one can show that they are indeed inverses of each other. So we'll try to see the analogous result for infinite Galois or more generally any Galois, any field extension. So to start this, we need the notion of a superfinite group. So let me start with superfinite group. So again, there are various equivalent definitions. So we'll stick to which is kind of more, more towards what I need to prove this fundamental theorem, and you can easily show those two definitions in detail. So I will say G is a profinite group. if it's inverse limit of a bunch of finite groups. So inverse limit, okay, so it's inverse limit. So if your collection of groups G alpha together with maps, so let's say if you have a bunch of G alpha with maps phi alpha beta is an inverse system. So what's an inverse system? If you have such things where these alphas are coming from partial ordered set, let's say G, such that for alpha lesser than equal to beta, these maps go from G beta to G alpha, such that if you have alpha lesser than beta lesser than gamma, then there are two ways to go from G gamma to G alpha, right? One, you can go directly by this map phi alpha gamma. And there is another way. First, you go from G gamma to G beta, which is just like this. And then you go by this. This is to comparison should match. So this is if you have a bunch of these things. So this G alpha is a group and phi alpha beta is just a group. If you have a system, it's called an inverse system. Sometimes a projective system. And in this case, we can define this inverse limit, which is nothing but denoted like this, which is by definition all those elements in this product G alpha. So these are direct product of these things, such that so basically this you can talk about the you can take the beta coordinate and you can go to alpha coordinate by this method. They should match with G. This so this should hold whenever alpha is equal to beta. That's an inverse limit of G alpha, and it's a profinite group if those G alphas are indeed finite groups. So these are kind of made up of finite groups, but they are not necessarily finite. As a trivial example, you can take, so say example 0. Any finite group is profinite, of course, because you can take all the G alphas to be that group itself. It's a finite, and all those phi alpha beta to be the identity. So everything will hold. It's an inverse system, and inverse limit is indeed just G alpha. Another example, which uh, more interesting, at least in context of this video, is if you have a Galois extension, Q over Q is Galois extension, uh, then this Galois group is a this is a profinite group, and the reason being its inverse limit of this is inverse limit of let's say L over K with L over K finite. This can be easily checked. So what you need, you just need to define a map from this to let's say you can define the map directly. Not directly, you can define the map here first. So what you do, you take a sigma. So it's a map from K to K. So you can restrict this map on each finite extensions of small k. So that will give me a map. And so there are a few things to do. This is 1 1. This is 1 2. And before everything, the image of this map is indeed the image of this map is inside the inverse. Injective is pretty easy to see because this map is non-identity. So this map says sigma is non-identity, so it will move some element alpha, right? So then you can look at L is just key small k join that alpha. That's a finite extension. And because it's moving, so the image of phi, sorry, the image of that element sigma under phi will not be identity. So it's an injective, right? Because it's the reason why it's not identity because it moves something in the alpha k alpha position, right? Because k alpha is a finite extension of little k, right? So that's how we can show it's injective, which is trivial. And this thing basically follows from finite Galois theory, which you can check. And surjectivity again follows similarly because what you start with a bunch of uh, element sigma suffix L for each finite extension L over key that is compatible because by virtue of one you already know the image lands inside the inverse limit. So those sequence whatever you choose should be compatible or in other words should form an inverse system. Then you can just glue those maps together because they will agree on the intersection because of the compatibility. So you can glue those maps to get a map phi from K to K, and by definition, the restriction on each finite L over Q will be that chosen element sigma suffix L. So it will be on. So that's again kind of true. So anyway, so it's an example, and the reason being profinite groups are kind of important because they occur naturally in most of the cases. Because these are the next thing, like finite groups are easy to handle somewhat. I mean, in terms of Galois theory and all, so the next best thing one can hope for is a profinite because this is somewhat made up of finite groups. Right? So, as an example, concrete example, I'm not doing just writing. So, in case you have a finite field, say FQ, which is between the R, P is a prime, of course, then this absolute Galois group, you can show easily it's just the profinite completion of this, profinite completion, whatever that means. Okay. And whenever you have a profinite group, you can define a topology on it. That's the important part because the correspondence theorem that we are going to prove in this video will involve that topology. So, and the topology is pretty easy to guess what it can be because so let me write topology of profinite groups. So, so what you do, you equip each GL for the discrete topology. So each GL is a finite. So discrete topology and equip this direct product of GL for the product topology and equip this inverse limit, which is the group G, the subspace topology, right? Because the inverse limit is indeed a subset of this direct product. So in this way, you can induce a topology of the inverse limit. And let me write some facts. I'm not going to prove otherwise. It will take some time. Although these facts are pretty easy to check. So fact one. So we have these projection maps, right? From this G to GL. Because G is indeed a subset of the product of GL. So we can talk about the projection. And one can show the kernel of these maps, these P alphas, from a basis of open neighborhoods of identity. Second thing is a closed subgroup of the product of G. And this will imply it's a compact because these G alphas are discrete topology. So these G alphas are having discrete topology. So they are, and of course, they are finite groups, of course. And their product is again a compact because product of compacts, this is a compact. And because it's a closed subgroup of a compact group by virtue of point 2, its compactness. So it's compact. Moreover, one can show it's totally disconnected. It's totally disconnected and it's housed off. Okay. And this open subgroups, so this inverse limit, this G is a topological group that's compact, totally disconnected, housed off. And its open subgroups are precisely the closed subgroups of finite index. So what does it say? So is that any open subgroup should have index finite and should be closed. And in fact, as I was saying at the beginning, that there are several equivalent definitions of profinite group. So one of them being, in some book they define profinite groups as a topological group that's compact, totally disconnected, and then they show that it's indeed a inverse limit of set of inverse system of finite groups. And in that case, actually, the inverse system, the candidates for the inverse system becomes the G modulo the basis of, so as I wrote, so this basis of open neighborhoods of identity. So in that case, they take G as the inverse limit. So let me write here in short. In that case, they write like this, where these EU are basis of open neighborhoods of identity. I mean, normal open neighborhoods of identity. Because the index should be finite, so each G mod U is a finite code. So in some book they define like that. It's a matter of choice. So now let's come back to what we were doing. So we were interested into Galois theory, and so everything that I wrote in these 4 points will go through exactly same for any finite or any Galois extension because as I just mentioned or sketched the proof that any Galois extension is a profinite group, the Galois group of the extension. So, so it makes sense. So it's equivalent topology. So it makes sense to talk about its closed subgroups. And the fundamental theorem so this says this is a Galois extension. Then on one side you take not all the subgroups but the closed subgroups of this Galois group. The other side remains the same. So these are sub extensions or intermediate extensions. Okay. So what we need, and now we have to do the map, right? So on one direction the map is same as finite case. So we need a map in other directions. So given an intermediate extension, how do you associate it with? So that's the fundamental theorem. And what you do is let me start with this claim because we need to associate a finite, sorry, it's closed subgroups. So claim, and maybe you can guess what's the closed subgroup. It's exactly the same. This is a closed subgroup of this whenever the lower k is finite. Or maybe you don't need anything finite because in this right hand side there is just intermediate extension. So whenever I mean it is an intermediate extension, right? So how will you show it? So to show it's a closed set. But in other words, its complement should be open. So just start with the point in the complement. Say sigma. So what does it mean? Sigma moves something in L, right? There is a system alpha, so the sigma alpha and alpha are different. So you take this open neighborhood. Take all this. So that when you restrict, uh, so not restrict. So this tau alpha is really this alpha set is maybe this tau alpha. So this is Dixon overall finite Galois extensions of small k. So one particular of them is k alpha, and you can also restrict sigma to k alpha. They should be same. Okay. So firstly, sigma belongs to descriptive. Secondly, descriptive is open inside. Okay. Thirdly, because you need it's an open, so any point in the complement should have an open neighborhood. That's uh, that is that is disjoint from this Galois group of Q over L, right? Because you're showing the complement is open. So and again, this is true for this as well, right? This because of this thing, but, because of this condition. So this should be empty. So what you do, you send L to this Q over L. So now you have maps in both directions, and you just have to show this the compositions are identity. So it's required. So let me call one of them map phi, then map psi. So it's enough to show phi psi is identity in respective domain. So I'm being a bit loose here. So and one of them, I mean, one of the compositions being identity will follow exactly same as for the finite Galois theory. So we'll see that next time, and we'll also see why the other composition is uh, identity as well. So proof was kind of similar. And if you want to find a counterexample why these closed subgroups are needed, uh, so there's you can search online notes of Keith Conrad. There he, I think, is given an examples where I think he took this extension, and there I think he took. I think there was two. I'm not. Can't recall it exactly, but I think what I saw sometime back, there were a couple of elements whose fixed field were the same, but the subgroup generated by them are different. So that's not a one-to-one correspondence. And indeed, later he went on to show that that element that he took, the subgroup generated by that is indeed not a closed subgroup. So for a counterexample, just you can Google Keith Conrad notes on Galois theory, you'll get this. So yeah, next time I will prove the compositions by their identities. So yeah, let me stop.